circuit switch and another is packet switch. Okay, I mean, if you have a circuit switch kind of a scenario, what kind of a switch you would be requiring, and if you have a packet switch kind of a scenario, then what kind of switch we expect to have. Okay, so for a scenario where you are basically having a circuit switch scenario, where you have n inputs and you should have n outputs, and both of them should be able to send the data from the corresponding input to the output port. Okay, so in that case the switch should handle n calls, where you have n logical inputs and n logical outputs. Okay, now how many calls can we basically I mean, can we have with this kind of a situation and with the limitation of our capacity? Okay, so it has been found out that n can be up to 200,000. Okay, now in practice, what do? We have studied about multiplexing and demultiplexing, right? So in practice, these input trunks are multiplexed. Okay, so for example, one trunk can carry one DS3 trunk can carry 672 simultaneous calls. Okay, so what does this multiplex trunk carry? We have already studied when we are doing multiplexing, we are basically getting a frame as an output, right? So the multiplexed trunks, they will carry frames which will be nothing but set of samples. Okay, so for a circuit switch, what should be the goal? That is, you extract samples from the frame, and depending upon what is the position of that particular sample in the frame, we switch to the output, corresponding output port. Okay, if you remember this diagram here, yes, this is the diagram. So this is the frame that you are getting, and you're putting samples here. Okay, so depending upon the position of the sample in the frame, we forward this sample to the corresponding output port. Okay, so that's what should happen in your in your circuit switch also. That is, you extract the samples from the frame, and depending upon what is the position of that sample in the frame, you switch it to the corresponding output port. So what is the need? That is, each incoming sample should get to the right output line and the right slot in the output frame. Okay, so we will see further bit more. So what is our objective? That is, we want to send the correct sample to the corresponding correct output port. Okay, now we have already studied that it is not possible for any switch to get to its full capacity, right? Why? Because we have the problem of call blocking. All right, so in case of circuit switches, can we get the problem of call blocking, or will we have the problem of call blocking? All right, so what is call blocking? Let me just revise once more. That is the scenario where you are not getting a path from the input port to the corresponding output port. Okay, so then whatever call you are making, whether I mean, whatever call or whatever data you need to transfer, then that needs to be blocked. Okay, so that is known as call blocking. Now it can be of two types, that is internal blocking and output blocking. Okay, so what is internal blocking? So internal blocking is that you have slot in the output frame, in the output, yes, the slots in the output frame that exist. Okay, they are free, but somehow there is no path from the corresponding input port to the corresponding output. Okay, so that is what internal blocking is. We will see some example scenarios for that also. Now we have switches which are classified as blocking or non-blocking. Now this definitely will depend upon what is the switch architecture and know what are the characteristics of that switch architecture. Okay. Next is the output blocking. So what is output blocking? That is, of course, no frame, no slot in the output frame is available. That means no resource is available. So therefore, your sample cannot be moved from the corresponding input to the output port. Okay, so this kind of blocking is independent of course, internal blocking, because internal blocking is happening when output frames are, or when slots in the output frame actually exist. Okay, they are free, but here the slot in the output frame is not available at all. So these are independent of internal blocking of the switch, and this can occur whether the switch is a blocking switch or a non-blocking switch architecture. In any case, output blocking can occur. Okay, because if you think of it, output blocking is happening when you have the scenario. If you remember the examples that I had given in a few last class, or maybe before that, I had given an example that suppose you are having a large amount of bursty data coming, and that is destined to a particular output port. Okay, so in that case, no matter what happens, that port is always going to be busy. So there will be cases where some other input port is having a particular data which has to be sent to that particular output port, but it couldn't be sent because of the scenario that that output stream is very busy with other samples which are arriving from other input ports. Okay, so that is the reason why it is being said that output blocking can occur even if the switch is having a blocking architecture or a non-blocking architecture. Okay, and then we have head of line blocking. I think I had gone through head of line blocking in computer networks basic course, so I would like to know about this from the students. So any BTech students who have recently done, like third year BTechs who have recently done the computer networks course, can you tell me what is the head of line blocking? Any idea?
The packets in the back of the queue is delayed due to the blocking, no path available for the first packet of the queue.
Yes, yes. So suppose there is, so I will show this with a diagram also later on, but um, as what is your name, please?
Kailash.
Okay. So as he just said, the about the definition of the HOL blocking. So basically, suppose there are many packets that are arriving at a particular input port, and they can be destined to different output ports. Now, because of output blocking for a particular output port, if a packet is blocked at the, which is at the head of that queue, then the packets which are at the back of that packet in the head, which are in the back of the queue, those packets may be destined to some other output port which is free, but still they are getting blocked because of the packet which is at the head of the queue and which is being blocked because of output blocking. So that is why it has been said that output blocking can cause head of line blocking. Okay, so this is what it is. Now, can we do something better, or what kind of switch can we have for a circuit switch scenario where we can still transfer the data in an efficient manner? So one of them is time division switching. Okay, so we will get to know what it is. So basically the key idea is that when demultiplexing, the position in the frame determines what is the output trunk. So we have seen in the previous example of a very simple multiplexer and demultiplexer that whatever way the samples are there in the frame, Okay, the position of that sample in that frame is determining which output port it is going, right? If you see the diagram, just I also showed now also that whatever the position of that particular sample is in the frame, that will be the determining factor of which output port it will go to. All right, so with this idea, the time division switch basically does what it does is it interchanges the sample positions. So look at this scenario. Okay, so these are telephone exchanges. Okay, this is the PBX A and PBX B. Now these are known as private branch exchanges. Okay, PBX. So private branch exchange A and branch exchange B. All right, now here what will happen, from your different telephone lines from different places in that particular area, you are getting all the samples here. So these are the samples that you are getting. You multiplex that and then send over the T1 line to the, so you have a TSI, that is time slot interchange, before a demultiplexer. Okay, in the basic multiplexer to demultiplexer, what was happening, from the multiplexer you are getting a frame which is having samples. Okay, and that is being sent as an input to the demultiplexer, which is simply checking that what is the position of which of a sample in that frame, and then forwarding it to the corresponding output port. Okay, but what will the this time slot interchange do? It will interchange the samples, position of the samples. Okay, so look at this as to what's happening here. So the multiplexer is basically getting this frame, okay, as an output. So it is giving out this frame as an output, where you are having these samples laid out like this in the within the frame. Now it is at the PBXB, it is going through the TSI, that is the time slot interchange. What is the time slot interchange going to do? It will change, or it will interchange the sample positions within a frame. Okay, so now you can see that the position of this sample, that is sample 2, is being changed here with 3. Okay, so now what is happening, that at the demultiplexer, these are the corresponding output ports are getting changed here. All right, so with this what would happen, that suppose there is some kind of sample which is having maybe it can be sent via another path, but it is having a higher priority, and you cannot wait for that sample to be blocked in any sense. So you just interchange those slots and then send them over through those ports which are quite free at this point of time. So this is how your time slot interchange basically works. Now if you remember, when we were talking about the router architectures, we were talking about the fact that whatever we are building as an architecture, we are always getting limited by some feature of that, some hardware feature of that, right? So what is that hardware feature? That how much of capacity it is going to provide, and with that how many line cards we are able to add to that system. That's what we had studied about router architectures. So similarly, with TSIs also, the question comes that how large can we make a TSI? Okay. Now, what will be the limitation here? So, of course, it will take time for RW. Okay, that is read and write to memory. Now, suppose you are taking 120,000 circuits. Okay. Now, your read write is going to take 2 operations. Okay, and it needs to be done. So it has been found out that for this example, that is if your voice is basically of 64 kbps rate, the sample size is 8 bytes and the rate is 8,000 samples per second, then the time that is required how much time after which you need to do a read write operation. That is, after every 125 microseconds per sample. That means after every 125 microseconds you need to do a read write operation. Okay, so now each operation takes around 0.5 nanoseconds, okay, for 120,000 circuit TSI. All right, so just imagine that every 125 microseconds you need to do this operation, which takes 0.5 nanoseconds, and that too for a 120,000 circuit TSI. Okay, so this becomes pretty complex, and with the technology that was there at that time, it became pretty impossible to do that. So what can we do? We can go for a better technique, okay, which does not need so much of task from the hardware side. Now let us see what is better than this. Can we do something better than that? Okay, now we are going to see the concept of space division switching. Now, earlier, all of you had asked me that you are not aware of what is space division switching. Okay, you knew about time division. Actually, this concept comes from, you must have seen time division multiplexing, frequency division multiplexing. So in frequency division multiplexing, what do? We generally have a channel, and then you divide it into small frequencies and then use it, so that simultaneously many users can use the same channel at the same time, but at different frequencies. That is FDM. Then for TDM, you are basically giving the entire channel for all the users, but you are changing the time for which they can use it. Okay, so that means every user is given a time slot within which they can use the use the channel. Now, what about space division? Okay, so space division, as the name suggests, has to do something with the distance between the users, right? So if two users are significantly apart geographically, then they can use the same channel, because that will not cause any interference of their data transmission. Okay, so this concept, I will give you one example of space division multiplexing. So you have seen radios, right? FM radios. So how does this work? Because when you go from one city to another, that radio Mirchi is still playing at that same frequency. I think it plays at around, I'm not sure, maybe 98.3 or 92.7. I'm not sure which frequency it is, but that radio Mirchi channel plays in every city, right? But it is playing different songs. The RJs are different, but the frequency is the same, right? How are they using that concept? That is, the cities, those cities are significantly apart geographically. So whatever this frequency is being used at this particular channel, it is not getting any interference from a neighboring city. Okay, so that is the concept of your space division. Now something similar is being used here with space division switching. That similar concept is being used here, but here of course you do not have the geographical distance here, because we are talking about a switch here. What you can have a different path here. All right, so space division switching, what is the concept that it is using? That instead of we were thinking about time slot changes, we were thinking about, can we have more and more number of paths? Instead of doing all of that, can we just change the path of each sample, that each sample within that particular switch? Okay, because what was happening, if somebody is getting blocked because of any reason, whether it is output blocking, HL blocking, okay, so if somebody is getting blocked, if we change their path to that particular to a different output port, or to that particular output port, so that they can take another path when they go out, and then reach finally their destination. So at least they are not getting that delay. So if we change their path, does it make the system more efficient? Okay, so that was the concept that or key idea behind this kind of a switching technique. So we have a space division switch. Now earlier when we were having the time slot interchange, we had the TSI before demultiplexing, right? So you had the samples from the multiplexer, and then that was sent over the T1 line to the neighboring PBX, that is PBXB, and then you had the TSI before the demux. Right here it is different. You have the sample coming in to the multiplexer, sent over the T1 line. The frame is being now sent over the T1 line. Then it reaches the demultiplexer. This is demultiplexed. And then finally the space division switching does its task by moving the samples within the frame through different paths to the particular output ports. Okay, so this is how this is working. All right, so look at this here. So you have the frame here. It is moved through the T1 line. You are getting the corresponding output here. Now this is sample 2. Okay, sample number 2 in the frame. So what was the idea that we have been using, that whatever the position of the sample is in the frame, it will go to that particular output port, right? But what is the SDS doing here? It is changing that path. It is not sending 2 to the output port 2, it is sending it to 3. Okay, it is changing that path. Now what kind of design will allow me to have such kind of a scenario? That means I should have something with a particular type of circuitry inside that will allow me to have a number of paths from some set of inputs to some set of outputs. Okay, this should be the architecture for a space division switch. Okay, because you never know which sample will come here, and then how will you work it out to the different output port. Okay, so now let us see this. So I think this diagram is known to all of you. We had discussed this in the last classes. So this is a crossbar switch. Okay, this is the design that can be there for a space division switch. This is the simplest form of architecture for a space division switch. Okay, so if you remember, it is basically a grid kind of an architecture, and you can have n input lines here, and these are m output lines. Okay, so you sorry, you can see that there is a path from one input port to different output ports. Okay, but of course it cannot be that, you know, if you send some data here, it will go to all the output ports here at the same time. That cannot happen because these are cross points. Okay, now this is a circuitry here. All right, so if you're using one path in this same I mean, suppose this is the same row and you are trying to use one path. So then here you will send the data. Okay, and the path will be made. So a path is made between an input and an output port if you are basically creating that circuitry between the two. Okay, otherwise there will not be any path for sending that particular data to that particular output port. Okay, so let me give you a little bit more explanation on these crossbar switches. As I already mentioned that crossbar switches are basically space division switches. Okay, so you can have n inputs and n outputs, or n inputs, m outputs, etc. So these crossbar switches have some active elements that are placed between the input and output lines. So as I was mentioning, that the circuit has to be made between, or the path has to be made between an input and an output line. Okay, how it is made? It is made with the help of some active elements which are at these points. These points are known as cross points. Okay, so in this diagram you can see that these dots are here which are having a circle around them. So these are known as cross points. Okay, so these have some active elements. Once you activate them, then only the path through that particular cross point is available to you. Okay, otherwise it is not available to you. All right, so that means these are placed between input and output lines, and the data will flow through a particular cross point only if it is active. Otherwise it is disconnected and the data cannot flow through that particular cross point. Okay, so now if your data is not multiplexed, then what you are simply getting samples, and you know that I mean you are simply getting the input and then you will send it to the corresponding output port. Okay, so it will connect the same input port to the output port lines. All right, so that is, you know, the simplest case where, and it is not efficient also because you are sending input one signal at a time and one sample at a time, and then you are just going to the corresponding output port. That's it. But what have we done in the previous classes, that if we want to send more and more data, if we want to make the system more efficient, we can use multiplexing in that case. So if your input lines are carrying multiplexed data, then your crossbar switch is going to be efficient for you. Okay, so what it will do, so now your line is basically going to carry a frame that has samples for different output ports. Okay, now what will the crossbar now have to do? So if you remember, when we were talking about the router architecture, and I had spoken just in the beginning of the router architecture classes, I had spoken about one thing, that there is a scheduler. Okay, there is a scheduler at the input as well as the output ports, which basically determines that which packet do we need to send depending upon its QoS constraints, that is quality of service constraints. Okay, so now similarly, if a multiplexer is multiplexing samples and sending it to the input of the crossbar switch, then the crossbar will also require a scheduler that will tell that which cross points to activate at each sample time, so that it can know that okay, which path to use, so that ultimately maximum amount of the crossbar's capacity can be used and the samples can be efficiently sent to their corresponding output ports. Okay, all right, so this is what I am trying to say, that you have large number of samples coming in at the input ports. So the task of a scheduler for a crossbar would be that which of these cross points must be activated for these particular input and output port combinations, so that you get, or your samples which are at these input ports, maximum of them are getting a path to their corresponding output ports, and you are making the maximum of the capacity that your crossbar can give you. Okay, so this is what the last point meant. All right, so now let's get to the problems, that is whether a crossbar is blocking or non-blocking. So let us see. So we had talked about two types of blocking, that is internal blocking and output blocking. Internal blocking, if a switch is, a switch can be either internally blocking or it can be non-blocking. That also we have studied. So crossbar switches are internally non-blocking. Okay, so what is that? That means no sample is blocked in the switch while waiting for an output line. Okay, so this is the feature of a crossbar. But what will be the problem? There still should be some problem with this, right? No system is 100% efficient. So what are the problems? The problem is that you have many cross points. If you have an input and n outputs, you have n square cross points for an n cross n crossbar. Now, what is the time taken to set? The time taken to set each cross point will go quadratically when you have samples coming in. Okay, so you have samples coming in your input ports, and the time taken that will so you will have to set each of the cross points active before you can get the path, and then before you can set the path for that particular sample to move from the corresponding input to the output port. Okay, now if you have n cross n crossbar switch, you will have n cross n square cross points, and therefore the time taken to set these cross points also grows quadratically when you are trying to find a path from the input to the output ports. Okay, so therefore this makes it expensive for large amount of n. Okay, and of course, as you are taking a large amount of time to set the cross points, your signal distribution time will also grow with n. Okay, now suppose there is a cross point failure. Okay, so a single cross point failure may isolate an input from a given output line. Okay, with that, of course, your crossbar will become less you know sorry, it should not be less robust to faults. Yes, it is less robust to faults, sorry. So it will make your crossbar faulty in that case. Okay, so this is the problem is that means your crossbar may be internally non-blocking, but it is complex because if you have n input and n output ports, you have n square cross points. So the time taken to set or make each cross point active, each required cross point active for sending the input to the output port, that grows quadratically. Now this makes the entire system very expensive when you have large n. Also, the signal distribution time will grow with n. Okay, and one other important thing is that if at all there is a cross point failure in your crossbar, then it might happen that an input port is getting completely blocked from its corresponding output line. Okay, so that is the problem that we have. So these are the problems basically that we have for a crossbar switch. So we need to find out enhancements on it or improvements on it so that these problems are not created. So one of the improvements or enhancements on this is multi-stage crossbar. So let us see what a multi-stage crossbar is. That is, in a crossbar, during each switching time, only one cross point per row or column is active. This is too much. Let me see the diagram. Okay. Let me show you the diagram and then show you how a multi-stage crossbar basically works. I will go back to the previous slide after this so that you understand the entire theory that is given. How a multi-stage crossbar works. What we were having in the previous crossbar, you just have n input lines and n output lines, and they are just connected with each other in a grid-like manner so that there are paths available from the input to the output port. Okay, but we saw that there are so many problems that can occur. All right, so what we are doing in multi-stage crossbar is that you have different capacity crossbars. Now, you have different capacity crossbar switches, and those switches you are basically connecting with other switches so that you are basically providing different paths for the samples that are entering your input side, and also you are avoiding the issues that you are getting with the cross points. That means if there is a failure, you still have another path to go through. Okay, so this is an example of a multi-stage crossbar. So I will show you how this crossbar is basically made. So the first set that you are seeing here, that is your input is also getting divided and it is being set into two sets of switches. Okay, so suppose you had 20 input lines, that is capital N is equal to 20. Okay, so you are dividing your inputs into two different sets here, where that is a set of 10. So small n is equal to 10 here. Okay, and then you are having array size. Okay, what is that for? So you have a 10 cross 3 switch here, that is the array size. That means how many of these stages can you have? Okay, so that is the array size. So now 10 cross 3 switch, then this 10 cross 3 switch is connected to a 2 cross 2 switch, and then the outputs of these 2 cross 2 switches are correspondingly sent through a 3 cross 10 switch. Okay, so this is an example of a multi-stage crossbar switch. All right, so here as you can see that the first stage consists of capital N by small n arrays of size n cross k. Okay, that means capital N by small n, 20 by 10, two arrays of size n cross k, that is 10 cross 3. The second stage consists of k arrays of size n by n cross n by n. Okay, so k arrays, k is equal to 3, so you have 3 arrays here, and each one of them is of size 2 cross 2. And then you have the third stage that consists of your n by n arrays of size k cross n. So you again have two of these switches with size of 3 cross 10. Okay, so now this is your multi-stage crossbar switch. Let us now see what are the features that this multi-stage crossbar is going to provide us. Okay, so in a multi-stage crossbar, in a general crossbar, what was happening, that during each switching time only one cross point per row or column has to be made active. Okay, now what your multi-stage crossbar can do, it can save cross points if a cross point switch can attach to more than one input line. Okay, so this is done using a multi-stage crossbar. So if you remember the cross points problem that I was telling you, that if there is a failure during a in a cross point, then it will basically block one input port to its corresponding output port. Okay, or two different output ports. Okay, so this problem may not occur in case of multi-stage crossbar, because you are basically allowing the switch, the cross point or the particular input port to get attached to different cross points. Okay, so basically one cross point can be attached to more than one input line. So therefore you can have a scenario that again one input line, if it is this situation will not occur, that if the cross point is having a failure, then you will not get any chance to send your data at all altogether. Okay, so this is done in case of multi-stage crossbar. So how it is done, as I've already shown you, that you divide the input into groups. Okay, and then you provide multiple paths between inputs and output groups, and they share a particular crossbar switch. And of course you need to rearrange connections every switching time, and therefore we need a switching schedule. Okay, so multi-stage crossbar does help in reducing the inefficiency that your crossbar switch, simple crossbar switch was placing. But the problem with multi-stage crossbar is that it is a little bit more complex than your simple crossbar, and you need to make more rearrangements by using your scheduler, and the division of this, how many stages that we need, each stage, how many switches, what should be the number of arrays, what should be the input and output size of those arrays. So those are important decisions to be taken, and that is a little bit complex here. So this is how your multi-stage switching can look like. Okay, so you have n inputs and n outputs, which are divided into um, groups here. So that is of n size. Now this is how I have already shown you that your stage 1 is having n cross k size arrays, and you have in stage 2 n by n cross n by n size arrays, but the number of that is k. Okay, so k number of arrays of size n by n cross n by n, and again there is stage 3, which is having n by n number of arrays of size k cross n. Okay, so here you have a total of 2nk plus k times of n by n whole square number of cross points. Okay, the number of cross points is more here, and you have more input ports getting associated to more number of cross points. Okay, so you do have paths from an input port to different output ports, and the blocking can be reduced in this case. Okay, so that is what I was talking about, that there are k disjoint paths from any input array to any output array, and if k is small, it is possible that an input and output port are both idle, but no path to connect to the two exists. That is, the switch can be internally blocking. Okay, that means if this array size, okay, if this is too small as compared to these two stages, then you might not have or then you might have a scenario that that your input and output ports, they are both idle, but there is no path internally to send from here to here. Okay, so it can be the situation when your k is small, so you have to choose k very wisely. All right, so I am repeating this once again. If your k is pretty small as compared to your input and output port size, what will happen, that there can be scenarios that maybe input port is idle, and input port does have some data, and it can send it out, it can be connected, and an output port, the corresponding output port is also free, it could have been connected with that corresponding input port, but because k is small, the path that could take this or that could connect this particular input port to the corresponding output port, that does not exist. Okay, because the k is pretty small. In that case, your particular switch can become internally blocking. So please remember, when we were talking about crossbar switches, simple crossbar switches, they were internally non-blocking, but when we are talking about multi-stage crossbar switches, in that case it is reducing blocking due to failure of cross points, but it can be internally blocking when k is small. So k has to be chosen pretty wisely. So yes, this is what the feature of multi-stage crossbar is. It can suffer from internal blocking, and unless k is efficiently chosen. The number of cross points is of course less than n square, but the cross points can be connected to more input ports. Okay, now finding a path from input to output port, how do we do that? The switch controller needs to find a path at the time of call setup. It uses path search algorithms such as DFS to find the path, and the path is then stored in the switch schedule. Okay, so therefore it does not have to again and again find out or search for a path every time there is a sample that is arriving for a particular output port. Okay, so these multi-stage crossbar switches, they scale better than crossbars, of course, because they are dividing the inputs, but still Not that great, because we need, for 120,000 call switch, we still need around 250 million cross points. So that is again too much. Okay, and then see, having just cross points is not too much. What is too much is that you have to find a switch schedule, you have to use a path search algorithm. So no, even if you try to store the switch schedule for a particular frame, but still there will be situations, which is most of the times, that what the data that is arriving for, that you need to have a schedule, and then find what should be the path to that corresponding output port. Okay, because they are all dependent with what is the input that is coming in the input port, and then what should be the corresponding output port, and that can vary for different input ports again. So with that, the path will keep varying from the input port to the output port, and therefore you do need to search, or you do need to use the path search algorithms more often than not, to find what is the switching schedule. Okay, so for a number that you can see, that is, if it is 250 million cross points, this is going to be too much. Okay, so scaling becomes too much even for a multi-stage crossbar switch. All right, so it is good but not that great. Okay, that's what it seems to be. So can we make any further changes in this? So with this uh, C loss or clause, I will call. So this is a researcher who showed one way that of improving these issues that multi-stage crossbars and simple crossbars were facing. Okay, so what was the problem with the multi-stage crossbar to begin with? The problem was that how much should be the value of k, so that my switch is internally non-blocking. That will still save a lot of data from getting delayed or getting dropped at the end. Okay, so Claus in his paper showed that that was too long ago, that was in 1953, that if we can rearrange, whenever a call arrives, if we can rearrange the connections, existing connections, that means we are simply rearranging the paths. With that, we will have a better condition as compared to the previous multi-stage crossbars. Okay, so what is the condition for that? So what he said is that if a switch controller is willing to rearrange existing connections when a new call is arriving, when a new call is arrived, with the condition is that k should be greater or equals to n. That is, the number of center stages must be greater than the number of inputs in a group. Okay, so the value of k is equal to 2n minus 1, and these could also be called as rearrangeably non-blocking switch. Okay, so basically he said that k should be greater than equals to n. That is, if you have capital N number of inputs and outputs. So if you have capital N number of inputs, then you divide it into a group of n. Okay, n inputs, and then you are making that a multi-stage crossbar, right? So if you want a better implementation of it, let us have the array size, that is k, which should be greater or equals to n, small n. Mostly k is equal to 2n minus 1. So with this, you can have, and you also have the property that the switch controller is willing to rearrange existing connections when a new call is arriving. So this kind of switch can also be called as a rearrangeably non-blocking switch. So with this part, the first point, that is k greater or equals to n, you are going to get a non-blocking, internally non-blocking switch. And also it will help out because you are basically rearranging the existing connections when a new call is arriving, so making it a rearrangeably non-blocking switch. Okay, so with this you have these many number of cross points, that is 2n times 2 small n minus 1 plus 2 small n minus 1 cross n by n whole square cross points, which is quite less as compared to n square, which was happening with cross points, simple crossbar switch. Okay, so this is what the CLOS network is. It seems very easy. that you have greater than n value of k, and you have the path, the existing paths. If you can rearrange it, it will not cause much of blocking. Okay, you will have an essentially non-blocking switch. But can we do this? And if we can do this, how can we do this? And what will still be the problems that will exist? Okay, that we have to take up in the next class, because the time is up for this class. So I will stop the class here. And okay, it is showing bad network quality for me. Did you guys hear what I said?
Yes, ma'am.
Okay.